Okay, so yeah, let's go ahead and get started. So what I wanted to do first is talk about the final paper. So the final paper is going to be due the final exams week. So anytime you want to give that to me, obviously, if you need more time to do it, reach out to me and tell me you need more time. I think final grades for grad students are due like the second week of January or something. So if you need extra time, please let me know. It shouldn't be a problem. I would like to have them finals week, but honestly, I probably won't get to them. I think that's Christmas week. So I'll probably be doing other things, but try to get it to me as soon as possible. So it's going to be very similar to our labs. So I'm going to create a GitHub repository, and you are just going to link your paper to that GitHub repository, and you're going to store everything on that GitHub repository, right? So your Cordo document, your Word document, PDF, whatever you decide to render your paper to. I want everything on there, and I want it to be completely reproducible. So all tables in your paper, all figures in your paper, I want to be able to reproduce them when I click a button. So make sure that it's reproducible. If you have any questions about the paper, or you run into any errors when you're trying to render the document, or just have coding questions about how to do certain things in Cordo, post them to the issues button or the issues area of the GitHub repository, and then we can have a conversation on there. And I think it's just easier to write code and copy and paste code doing that than by email. But if you do want to email me questions, you can do that as well. But I might just tell you to post it on your repository. Are there any questions about the final paper? Hopefully you guys have started your final paper. But there's 2 weeks for you to write the paper. Again, I want it to be very short. I don't want a 20-page, manifesto, 30-page manifesto, a couple paragraphs for your introduction. I want a longer kind of methods, results type section, because this is, a stats course, and then, a couple paragraph discussion. So I don't think that it should be too hard. Again, I want you to, start thinking about some ideas for future projects, right? And then this will help you hopefully get started on that. So that's kind of the idea. Yeah. Yeah. Yep.
Is there anything different from that? I mean, other than, I imagine, I don't know, like with the introduction, for example.
Yeah, so I mean,
you've already written the paper, like.
Well, yeah, so like I would probably state like, okay, I'm reproducing this particular paper, right? And then maybe talk a little bit about like what they found, and then go into your analysis. And obviously you'd want to link like what you found compared to theirs, or any type of a new additional analyses.
Okay.
And then also for just reference for the actual paper itself, if you go to the syllabus, I do have a pretty lengthy write-up of what I'm looking for in the paper. So you can also refer to that in terms of like what I'm looking for in the paper, and like the sections that I want. But yeah, again, pretty flexible as long as you have the parts and it's reproducible. That's really all that I care about. But any other questions about the final paper? Again, feel free to send me emails, post an issue on the repository. I'll probably get that up by Wednesday. So if you want to start working on that, you can by Wednesday. So for today's lecture, if you want to follow along, so I didn't do that last week and I apologize. So I have a link now so you can easily access the Cordo document if you wanted to open it up in RStudio and write notes. Some of the packages that we're going to be using today. So to kind of recap what we went over last week, we started talking about moderation and interaction. And specifically, we talked about continuous by continuous interactions and continuous by categorical interactions, right? And a moderation effect is essentially when the effect of X on Y depends on some third variable. So the relationship between X and Y is modulated by some type of third variable, and that's sometimes called a moderator. And what moderation tells us is about the conditions that facilitate, enhance, or inhibit the effect. So it can tell us if the effect is large versus small, so large in one condition and small in another. It can tell us if an effect is present in one condition and absent in another. And it might tell us if it's positive in one condition and negative in another condition. So that's moderation in a nutshell. What I want to spend time today talking about is categorical by categorical interactions, which I think are a little bit more complicated than the categorical by continuous and continuous by continuous interactions. So I want to spend the entire class period talking about these. So to help us, I want to use a data set from LaPaglia, Miller, and Protexter from 2022. In this particular study, they were interested in a lot of different things, but what we're going to focus on today is the impact of instructor fluency. So they had an instructor record a lecture, and that instructor acted fluent, right? So made eye contact, wasn't disorganized, was moving around, had good posture. And then they also recorded a video where they were disfluent, so they're looking at their notes. They weren't, providing eye contact or kind of slouched over. And then what they did is they manipulated the gender of the instructor. So they had a female and male both record fluent and disfluent videos. And what we're going to look at is just how this influences performance on a quiz. So is there an interaction between those two things? In this study, they had 72 participants, 49 females and 23 males, and they used a 2x2 design. So let's go ahead and let's load in the data set. So what we need to make sure is that our two categorical variables, gender and fluency, are both factors. And then what I also did here was I changed the name of the one in the columns from quiz score to quiz. So let's go ahead and just run that code here. Make sure all of our ran. So yeah, so we have subject number, we have gender, fluency, and quiz. So we have all the columns that we need. So what they used was a 2x2 factorial design. So what is a factorial design? It's basically a case where we have more than one factor. So more than one factor is manipulated. And the most common is a two-way factorial design where we have two factors. You could do a three-way design where you have three factors. You could do a four-way, a five-way, a six-way. I think that if you're trying to do something greater than a three-way, don't. The more factors you have, the larger sample size you're going to need, and it's just completely insane. So I would say try to stay away from four ways and five-way interaction if you can, and try to break it down to something a little bit more manageable. So explaining a little bit more about the data set that we're using. So in this particular study, they had two factors. One was gender and the other one was fluency. And there's two levels to each of those factors. So for gender, there is males versus females. And then for fluency, there was disfluent versus fluent. This is a fully cross design. So that means that each level of one factor is tested with every level of the other factor. In this particular case, we had a male disfluent condition, a male fluent condition, a female disfluent condition, and a female fluent condition. And there's a total of 4 cells or 4 groups that we tested here. This is a two-way between subjects ANOVA. And to get the number of cells that we have or the number of groups, we just take A times B. So the number of levels in A times the number of levels in B. And generally, when we're looking at these two-way ANOVAs or two-way designs, we're interested in main effects of gender, the main effect of fluency, and we're also interested in the interaction effect between gender and fluency. So you might be asking, what the heck is a main effect? So what I want to do is I want to differentiate main effects and compare them to simple effects. So a main effect is essentially marginal mean differences. So what that means is that we're looking at the mean differences within a factor, ignoring the other factors. So to make that a little bit more concrete, what I have listed here are just the cell means. So these are the means for each of our groups. For each row, we have a gender. So female is one row and male is another row. And then we also have fluency for each column. So disfluency column and then a fluency column here. And then we have all of the means for each of our conditions here. So what does it mean when I ask, what is the main effect of fluency? Well, what we have to do is we have to look at these marginal means for the columns. So we have a marginal mean for the disfluency condition and a marginal mean for the fluent condition here, right? So 6.10 and 7.92. These are the marginal means. So this actually collapses or averages across female and male, right? We're collapsing across that. All we have is a mean for disfluency condition and a mean for the fluent condition. That's what I mean when I say main effect of something. So main effect of fluency. What about a main effect of gender? So here we're going to look at the row means here for female and male. So female has a marginal mean of 7.27 and male has a marginal mean of 6.75. These means are averaged over the disfluent and fluent columns here, right? So we average these and we average these. So essentially we're kind of ignoring them to get our main effect of gender. So how does this compare to simple effects? So simple effects are conditional mean effects. And what we usually look at are differences between the conditions or cells. So if we look at our table here, we have our means for each of the conditions, right? So for the female disfluent condition and the female fluent condition, as well as the male disfluent condition and the male fluent condition here. And simple effects compare the means of each of these cells to one another, right? So maybe we want to compare female disfluent group, which is 6.69, to the male disfluent group, which is 5.50. Those are simple effects where we compare the differences between conditions or cells, which contrast to main effects. So everyone on the same page, understand the difference between main effects and simple effects? Thumbs up, yes. So now let's talk about dummy-coded categorical by categorical regression. So when we do a regression model with dummy-coded categorical predictors, we're basically testing the conditional effects and not the main effects. And this is so vastly important because I see this all the time in papers. People do not interpret these type of models correctly. So it's important that we understand what these coefficients represent. Again, conditional effects, not main effects. So if we're going to run a categorical by categorical regression model, right, with dummy-coded categorical predictors, B sub 0 is going to be our intercept term, like it always has been. It's going to be the predicted outcome when both x and z are equal to 0. So whatever we have dummy-coded 0 for our predictor variables. B sub 1 is going to be the mean difference in the intercept for a 1-unit change in x. And this is the predicted change in y at z equals 0. B sub 2 is the mean difference in the intercept for a 1-unit change in z. And this is the predicted change in y at x equals 0. And B3 is the interaction term, similar to other regression models that we've fit. So this is the interaction of x and z, or the offset or mean difference in z for a 1-unit increase in x, or we can just flip that, the offset or mean difference in x for a 1-unit increase in z. It doesn't matter. So let's go ahead and fit our categorical by categorical regression model, our two-way regression model with dummy coding. So we can manually dummy code our variables and select our levels, what we want to be 0, what we want to be 1. But as I said before, R does this automatically for us. So we're just going to have R do this. Both gender and fluency are already coded as factors in our data set. So we can just go ahead and run it and it'll dummy code it for us. So if we run our regression model here, we have an intercept value of 6.69. So let's go through each of the coefficients and let's just basically interpret each of those coefficients. So in this case, what does 6.69 represent here?
What's our outcome variable then?
So the outcome variable is quiz performance.
Just the quiz performance when our two factors are at 0, which is gender and fluency.
Yep.
I don't know which 0 is, because that's like dumb.
Yeah, so 0 here is going to be, so if we're talking about gender, 0 is female, and then 0 is disfluent condition. But yes, correct, Abby. So it's the predicted.
They do it like alphabetically.
Yeah, do it alphabetically, correct. Yep. So it's the predicted value of y. So our outcome measure here is just performance, our quiz performance when x equals 0 and z equals 0. So this is basically the mean value for the female disfluent group. Right? So that's what 6.69 represents. That's basically our mean value for the female disfluent group. what about this gender M term? So this would be our B sub 1 term, right? So this is our gender effect. How do we interpret this? So what does this negative 1.19 represent? So remember, the intercept is for the female disfluent group, right? So female is 0 and disfluent is 0. What does this gender term represent? Yep. When fluency is 0. Yep, correct. Yeah, so this could be interpreted as a simple effect of gender when z equals 0. So another way to state this is the mean difference between males and females in the disfluent group, because z equals 0 here. Excellent. So that difference is negative 1.19, and we could take the intercept, and then we could add this negative 1.19, and we can get our mean, the mean for the actual male group in the disfluent condition. And I'll show you how to do that in a bit. All right, so what about B sub 2 here? This fluency fluent coefficient. So it's a difference between something. So what's the intercept again? Female disfluent. Yep. So this is the difference, right? Or I guess we could say the simple effect, excuse me, fluency, right? When x equals 0. So when x is female, right? So this would be the difference between the fluent and disfluent condition for females, right? So essentially what we could do is we could use this estimate and we can get our female fluent mean by doing some algebra here, or some basic math. All right, what about the last term here, B sub 3? This has a similar interpretation to an interaction at categorical by continuous, and even a continuous by continuous interaction. So this is just the interaction between gender and fluency, right? Another way we can state this is that it's the mean difference in gender for 1 unit increase in fluency. Another way we can state this is the mean difference in gender for the fluent condition minus the mean difference in gender for the disfluent condition. Again, this is our interaction term. And we would look at this term to see if there is an interaction in our model. So to kind of summarize what I just typed out here, the intercept in this type of model represents the female disfluent instructor condition, which has a mean value of 6.69. The B sub 1 term is going to be the female minus male when disfluent, so in the disfluent condition. And we can just take the mean values for the disfluent condition for males and females and get our estimate of negative 1.19. B sub 2 is the fluent minus disfluent when female. Again, we can look at the female groups and then we could take the fluent minus disfluent and get the estimate from the table. And then our interaction term is just the male minus female when disfluent minus the male minus female when fluent. So this is our interaction term. And we could just take the means and we can subtract them and then get our interaction estimate here. So what we can do is we can take our dummy coded variables where we have female equals 0, right? And male equals 1 because R automatically assigns this alphabetically. For the fluency condition, we have disfluent as 0 and fluent as 1. What I have here is are these columns D1 and D2. This is just the dummy coding for gender and then dummy coding for fluency. And then the interaction is just multiplying D1 times D2. And what we could do is we could take these dummy coded variables and we can input them into our regression model and we can derive the means for each of our cells or our conditions here. So for the female disfluent condition, we can look at the first row here and we can input 0 for B1, 0 for B2, and 0 for B3. And essentially all we're left with is B sub 0. So that's going to be our intercept value, right, from our model. If we want to know the mean for the female fluent condition, we can look at the second row here and we can input 0 for B1, 1 for B2, and 0 for B3. And the female fluent condition is just B sub 0 plus B sub 2. If we want to know the mean for the male disfluent group, we have to look at the third row here and we can input 1 for B1, 0 for B sub 2, and then 0 for B sub 3. And the male disfluent group is just B sub 0 plus B sub 1. And then if we want to know the mean value for the male fluent group, we can look at the last row here and just input 1 for B sub 1, 1 for B sub 2, and 1 for B sub 3. And the male fluent group, the mean, is just B sub 0 plus B sub 1 plus B sub 2 plus B sub 3. So that's a lot of work. And luckily we have M means that will do this for us. So you don't really have to, look at the actual output and, try to derive the means from that. So we can just run M means, and M means will give us the means for each of the conditions for us here. So we can use the M means function. And what we have to specify is we have to actually specify the interaction between gender and fluency to get the means for each of the conditions. So that's why I have this little asterisk here. And then we can get our means here. And again, right, female disfluent is 6.69. That represents our intercept. And then we can also do some math here and get the other means by plugging in things. And we can also get our coefficients as well by subtracting them if we wanted to. All right, so that's regression with dummy coding. And that gives us simple effects, conditional mean differences. We often don't want that. Oftentimes we want main effects. So what are the differences between gender? What are the differences between fluency? And one way that we can get that within a regression framework is by using deviation coding. So what we're going to do is we're going to take our categorical variables and deviation code them. So for fluency, we're going to code them 0.5, negative 0.5. For gender, we're going to code them 0.5, negative 0.5. And if we fit this deviation coding model, the coefficients change in interpretation. B sub 0 is now the overall mean or the grand mean. B sub 1 represents the main effect of the factor A. B sub 2 represents the main effect of factor B. And B sub 3 is going to be the interaction effect. So let's go ahead and contrast code or deviation code. This should not say some code. So let's go ahead and deviation code our two variables here. So the first level is just going to get a 0.5. The second level is negative 0.5, and we're going to do that for both gender and fluency. And then let's go ahead and just rerun our regression model here. So if we rerun our regression model here, we get a new set of estimates where the intercept represents the grand mean across all the cells. Gender 1 is now the main effect of gender. So are there any differences between gender? And here we get a p-value of 0.29, so it's greater than 0.05. So there is no gender differences. Fluency 1 is our main effect of fluency, so the differences between the fluency marginal means. And here we do get a significant effect, so p is less than 0.05. And then gender 1 and fluency 1 is going to be our interaction term, which is similar to our dummy coded regression. And here we do not see an interaction between gender and fluency. So all we really have here is a main effect of fluency. So this is just a summary of the interpretation that I just gave. So our intercept is our grand mean, which is 7.01. B sub 1 is going to be our main effect of gender, so female minus male. So we could take the marginal means for females minus the marginal means for males and get our coefficient estimate of 0.52. That's the difference. We can look at B sub 2, which is going to be our main effect of fluency, or fluent minus disfluent. So we can take the marginal mean of the fluent, subtract that from the marginal mean of the disfluent, and get our difference, which is 1.83. And then the interaction term is the same as if we fit a categorical dummy coded regression, which is just the difference. So the gender difference for disfluent minus the gender difference for the fluent condition here. So in our particular case, we only saw a main effect of fluency. So in terms of visualizing these effects, if you have a main effect and no interaction, what you'd want to visualize is the main effect. So what I have here is just a visualization of our main effect of fluency. And what do we observe here? The individuals that watched the fluent condition did better than when they watched the disfluent lecture. If we did have an interaction effect here, we'd want to visualize that interaction. So here I'm just doing rain cloud plots, but you could use whatever visualization techniques we talked about. This is just one way to visualize the data. But again, hopefully we can see here, there's not really much going on here between fluency and disfluency. The effects are fairly constant, where we have the fluent condition doing better across gender, whereas disfluent is doing poorer. So no interaction here. So are there any questions about dummy coded regression versus deviation coded regression and the interpretation of those coefficients?
Is it common to deviation code? To me, that seemed like more straightforward.
Yeah, it's common to do deviation coding. So again, if you have specific predictions or hypotheses about cell means, then you could do the dummy coding. But again, I think it makes it more complicated, right? Because I think for the most part, we care about like main effects of gender, main effects of fluency, or just main effects in general. So it's fairly common when we have this 2x2 design to use deviation coding, I think. And as I've kind of talked about already, right? So the relationship between ANOVA and regression. So when we're fitting an ANOVA model or a factorial ANOVA, it's basically a special case of our deviation coded regression, right? And because of this, I wanted to spend a little bit of time talking about the ANOVA and how we can run an ANOVA in R, but also I want to talk a little bit about conceptual issues as it relates to ANOVA. And another reason why I wanted to talk about this is because in a 2x2 design, run a deviation coded regression model, and life is going to be good. However, when we start dealing with things like 2x3, or a 2x2x2, or a 2x2x2x2, the regression output is just going to become uninterpretable, right? Because we have all these conditional effects, right? So my suggestion is to just fit an ANOVA model. And I know that's shocking, because all this time I've been saying, don't run an ANOVA. But when we're dealing with these categorical predictors, I feel like for interpretability purposes, running ANOVA is just going to make your life a lot easier. So I wanted to show you a package that you can use to run ANOVAs that will make your life a lot easier, and how to interpret that. But we've kind of already been talking about ANOVA, this entire semester. So hopefully things won't be too complicated. So far we've kind of worked with the one-way ANOVA approach, right? So we fit our regression model and we have that F test. We looked at a categorical predictor, one categorical predictor that gives us an F test. With a factorial ANOVA, we just have more F tests, right? Conceptually, they're similar. We just have more of them. And that's what I've highlighted here, right? So since we have three effects, right? Two main effects and an interaction, what we're going to do is we're going to compute f-tests for each of the factors. So here we're going to compute an f-test for the gender factor, right? Which we're going to take the mean sum of the explained error for gender and divide that by the error or the unexplained error for the factor of fluency. We're just going to take the mean square explained error for fluency and divide that by the total error or the unexplained error. And then for the interaction, we're going to take the mean sum square explained error for the interaction divided by the unexplained error. That's essentially all we're doing. We're conducting f-tests for each of these factors. So we can kind of think of this as several one-way type of ANOVAs, but we're doing them all together.
Is the f-test in the linear ANOVA?
Yep. So you know how we've been computing the f-test, right? Where we're just making inferences from that one f-test. We're just doing that like several times now, where we're going to compute it. So like, let's say we just have one categorical predictor. We calculate an f-test. Now we have three, and we're just going to run separate kind of f-tests for each of those factors. So because we have three f-tests, we have three null hypotheses to test, right? So that's what we use the f-test for. So we have a hypothesis related to gender, and that hypothesis relates to the marginal means or the marginal row means here. So mu sub 1 and mu sub 2 here, right? So that's essentially what we're testing. And the null hypothesis here is that there are no differences between mu sub 1 and mu sub 2. And obviously, if we had more mu's, then we would say that there's no difference between those mu's. The alternative hypothesis is that there is a significant difference between those mu's. And that's what the f-test helps us assess. If it's statistically significant, then we can say that there are differences between those mu's. If it's not, then we can fail to reject the null and state that there's no statistically significant difference between those mu's. When we're looking at the main effect of fluency, basically we're testing the null hypothesis for the column marginal means, so mu dot 1 and mu dot 2. The null hypothesis is that there's no difference between those two, whereas the alternative hypothesis is that there is some difference between those mu's. For the interaction term, essentially what we're testing is if there are any mean difference between the conditional or cell means. So this mu11 and mu12 and mu21 and mu22. So the null hypothesis is that there's no differences between those cell means, and the alternative hypothesis is that there is some difference. Sometimes when we are looking at different factors, they might use different Greek symbols. So for factor A, they might use alpha, and for factor B, they might use beta. So you might see that interpretation in some of your readings. But just note that we're just looking at the null hypothesis of no cell differences versus the alternative hypothesis that there is some type of difference between those cell means. So if we remember, when we are conducting an ANOVA, it's all about the partition of variance or the partition of sums of squares. So essentially we have our sums of squares total, which is a combination if our design is balanced. So there's equal n in each of the cells. It's just the combination of our sums of squares unexplained error with the sum of squares for our model. And that is partitioned into the sums of squares for whatever your factor 1 is, sums of squares for whatever your factor 2 is, and then the interaction between those two. So in our case, sums of squares for gender, sums of squares for fluency, and then the interaction between gender and fluency here. And these are just kind of the how you would get the sums of squares for each of these components here. So let's go ahead and run an ANOVA. And there are lots of different packages that we can use to run an ANOVA. So there's SuperANOVA, and we've used some other ones like AOV and then the ANOVA function. One package that I really, really like is the AFAX package. And that's the one I want to highlight. And hopefully you will continue to use the AFAX package. And there's a couple reasons why I like the AFAX package. One is I think the syntax is pretty straightforward and simple. So we have this AOV underscore EZ function. And all you really need to do is put in the subject number, your between factors, and this could be extended to within factors. So if you have within It can also be extended to mixed models. So if you're doing multi-level modeling, there's lots of flexibility within this kind of AFEX ecosystem. We list our DV, the data, and then we can also have it output an effect size measure. So here I'm just saying PES, which stands for partial eta squared. Another reason why I like this is that there's lots of useful functions. One of those functions is called AFEX plot. So essentially what you can do is you can just take your model, run it in with the AOV_EZ function. And basically you could just feed it into this AFEX plot function and it'll just output kind of a nicely formatted plot for you. And then you could use ggplot syntax to like clean it up a little bit. But I think that this package is wonderful and I really love using it. I think it's easier to use than some of the other ones. So that's why I wanted to highlight it. So if we go ahead and we run our ANOVA model with the AOV_EZ function, we get output that looks like this. That's kind of cleaned up. This should be kind of all familiar to us, right? This is an ANOVA table. In the first row, we have our gender effect. This is the main effect of gender. And we see that the p-value is not significant. We can look at the second row. This is the main effect of fluency. We have our f-test, we have our partial eta squared, and we also have our p-value, and this is less than 0.05, right? So this is significant, which matches what we found with our regression. And then the last row is the interaction between gender and fluency. And here our p-value is 0.176, so it's not statistically significant. So again, similar inferences from our regression model. And just to show you that these are essentially the same thing, I also ran a deviation coded regression model. So where gender and fluency are deviation coded with 0.5, negative 0.5. And what we can see if we compare the two is that we get essentially the same p-values, right? So for the gender effect, 0.29, we get 0.29 here for the ANOVA. For the fluency effect, we get less than 0.001. That's what we get for the ANOVA and so forth and so on. Now, we do notice that there's differences in the statistic, right? So with a linear model, we're using a t-test. And within ANOVA, we're using an f-test. But something really cool is that we can actually square this statistic here, and that gives us our f value. So if we square 1.06, we get 1.12. If we square negative 3.73, we get 13.92. So again, these are equivalent to one another in the 2x2 sense, or a 2x2 design. So we don't have a significant interaction here. We only have a significant main effect. But for funsies, let's just pretend that we have a significant interaction. So when you have a significant interaction, you want to follow that up with what are called simple effects analysis, right? So similar to simple slopes analysis. So with the simple effects analysis, we're going to look at one factor at the different levels of another factor. In our example, we're going to look at the gender difference between the disfluent condition and the fluent condition. And what we're going to do is we're going to calculate two F values. The first F value is going to represent the gender difference at the disfluency condition. And then the second F value is going to represent the gender difference at the fluent condition. And essentially all we're doing here is we're looking at the mean square explained error for gender in the disfluent condition divided by the overall error. That would give us one F value. The other F value would be the mean square explained gender error for the fluent condition divided by the overall error. And we're using the overall error here because that's preferable because we're fitting the whole model. Sometimes individuals like to perform t-tests, and I'll show you how you can do that. So you can perform a t-test if you'd like, again, in this simple type of design, but oftentimes people don't use the whole model error, which is problematic. So we need to make sure that we're using the model error to get the correct F values or the correct T values. So how can we perform that in m-means? So what we could do is we could use our m-means function that we've already used before, right? Where we're looking at the interaction between gender and fluency. And we're going to add this pairwise function here. And what's key here to get our f-tests is we have to use this joint test function from m-means. And we're saying that we want these f-tests by fluency. So we're going to get an f-test for the gender difference for the fluent condition, and then the gender difference for the disfluent condition. So if we go ahead and run that in our console, this is the output that we get. So we have our gender difference for the disfluent condition, and then the gender difference for the fluent condition. We have our f values and we have our p values. Here, the p-values are not significant in either case, which is not shocking because there was no significant interaction here. So when we're reporting these things, we would report the f value, right? So our degrees of freedom 1, and then degrees of freedom 2, and then our p-value for each of these. So this is how you would report it. So there is no gender difference for the fluency condition, nor is there a gender difference for the disfluency condition. And if you had a particular hypothesis, you could, again, flip these, and you can look at the fluent condition, or the fluency effect for males versus females. You could do something like that. And to do that, you would just change this. Do something like that. If you wanted to flip it, you could do something like that. Now here we do see a difference for males in the fluency condition, but again, there is no interaction. So we would not follow this up. No interaction, don't do the simple effects analysis. Interaction, do the simple effects analysis. So as I stated before, some people, and you'll probably see this reported quite commonly, I don't actually see the F values reported for simple effects analysis a lot. Most of the times I see the t-test reported for that effect. So here we can use the pairs function, which we've used before in the past, and this will give us our t-tests. So we can look at the contrast between females and males, right, at the disfluent level, and then the gender difference at the fluent level. So instead of an F value, we get a T value here. And personal preference, whatever you'd like to use, go ahead and use that. But again, we would get similar inferences here, right? The P values are essentially the same. So we have to make sure that when we're reporting our results, that we also append an effect size measure to that report. So commonly we use partial eta squared in a situation like we have with the current data set where there's not a lot of participants per cell. We do something like partial omega squared. And if we're using the AFEX package, you can easily report those because you can get them produced in the output. If you don't use the AFEX package, there's lots of other packages you can use. The one that we've used before is the effect size package, and it has an eta squared function. And we can just basically run our model, deviation coded model, and then and it will output the eta squared values for us. And then this is what we would report in our paper here. So again, we get our eta squared our partial eta squared for gender, fluency, and the interaction. And that's what we would report. For our simple effects analysis, what we'd want if we're going to use F values or the F tests, make sure we report eta squared with those simple effects analyses. Here I'm highlighting a package that will, a function that will allow you to take the F values from that test and then transform them into partial eta squareds. So if you remember, we had two F values. One was 2.91 and the other one was 0.05. Degrees of freedom is just 1. And then our degrees of freedom error is 47. That can all be gotten from the actual summary output from m-means. And then we could just get our partial eta squared values here, and then it gives us our confidence intervals. If we're going to use t values, we want to use Cohen's d for those t values. And here there's a t to d function where you can take the t values from those t-tests, make sure you're using the correct error for the overall model, and then it can output the d values for you for those comparisons. All right, so are there any questions about simple effects analysis or ANOVA in general? Have any of you used the AFEX package before? No, it's a good package. Hopefully you'll use it going forward. I love it. All right, so this is where things get weird and complicated. So far we've been talking about sums of squares kind of in general, right? We take these sum of squares and we partition the variance in an ANOVA model. And this is all fine and dandy if we have a balanced design. So when I say balanced, what I mean is that in each cell of our design, there's an equal number of participants. However, things get really complicated when we have an unbalanced design. So that means that there's unequal participants in our cells. So if we look at this particular data set that we're working with, right, we have 13 in each of the cells except for the male disfluent group, they have 12. So this is not horribly unbalanced, and the results probably won't change too much, but it could be common where we have, lots of missing data and unequal cell sizes, and that could cause some problems. So I really want you guys to just be aware that when we have unbalanced designs, the sum of squares can be partitioned differently. And there's different types of sum of squares. And it's really important that you read the documentation for these models that you're running to see what type of sums of squares are being run, because there's defaults, and what type of sum of squares you should use for your own design, for your own data. So I wanted to talk kind of in general about 3 types of sum of squares. There's sequential sum of squares, which are sometimes called type 1 sum of squares. There's type 2 sum of squares, which are hierarchical. And then there's simultaneous sum of squares. So I want to go through each of these in turn. So if we're going to use just the generic AOV base R ANOVA function, by default, that uses type 1 sum of squares. And type 1 sum of squares are called sequential sums of squares. And the reason why this is because it assigns variation in order that they're listed in your model. So let's say we have a model with gender first, we list gender first, then fluency, then the interaction between gender and fluency. What type 1 sum of squares is going to do is first assign maximum variation to variable A, which is gender, then the remaining variation to B, then to the interaction, and then the rest goes to the error, the residual sums of squares, or the residual error. And if you have an unbalanced design, it's preferable not to use type 1 sum of squares. And the reason for this is because you can change the order in your model, and that's going to change your results. So if we had fluency, gender, and the interaction, we would get a different set of sum of squares, and we could get different effect sizes. And it could also change the statistical significance. So that's something to be aware of. And that's why it's generally recommended not to use type 1 sums of squares. Not sure why it's the default, but so one thing I did want to mention is that in a case where everything is balanced, when you have equal cells, type 1, type 2, type 3 sum of squares, it doesn't matter what you use. You get the same results. It only matters when you have unbalanced designs. That's why, we harp on having equal cell sizes, right? So it's important to try to make things as balanced as possible because it makes your life easier. So we can highlight type 1 sums of squares kind of in a modeling type of approach, right? Where we compute the F value, right? The F value is basically a comparison of 2 models. So for the main effect of gender, what essentially we're doing when we're ascribing or when we're allocating variance to that particular factor is we're basically comparing a model with gender in it to a null or restricted model with just intercepts only, right? So nothing in the model. We can compare those 2 models and we get sums of squares for gender, and then we also get our F statistic and our p-value associated with it, right? So think of the ANOVA table, that would be the first row of our ANOVA table with degrees of freedom and our sums of squares. What about for fluency? So hopefully you can see now the sequential nature of type 1 sums of squares, because now we're building off this model, right, with just gender in it. And now we're running a full model with gender and fluency in it. And we're comparing these 2 things. And when we compare these 2 models, we can get sums of squares for fluency, which is 41.88. And then we get associated p-value and F statistic associated with that. Then we can look at our interaction term. We're going to build up sequentially, right? So we're going to have a model with just gender and fluency, and then we're going to compare that to a model with the interaction between those 2. We can calculate an F-test between those 2, and we can also calculate sums of squares for that interaction term, which is 5.77. We get our F value and we get our p-value associated with that. We can put this all together and we get a nice ANOVA table that we all are used to seeing, with each row representing the main effects for gender and fluency and the interaction effect. So again, with type 1 sums of squares, it's sequential. We start out with nothing, we add gender, then we add fluency, and then we add the interaction. And that's how we're allocating the sums of squares or the variance explained by these factors. There's type 2 sums of squares, and type 2 sums of squares allocate variance to a particular factor only after the other factor has been taken into account. And what's important to know about type 2 sums of squares is that it only tests the main effects and it ignores the interactions. So what we're essentially doing is for factor A, or gender in this case, right? We're allocating variance to A after accounting for B. And for factor B, or fluency in this case, we're allocating variance to B after accounting for A. And I came up with some Venn diagrams to hopefully explain this in some type of digestible manner. So essentially what we are doing is starting off with these two effects, right? Gender and fluency, and they overlap, right? So there's overlap in variance. What we're doing is we're basically subtracting gender from this, and then what we're left with is the sum of squares for fluency, so the explained variance in fluency. The same thing for gender. We start off with these two effects, fluency and gender. We subtract fluency from that, and then we're left with the sums of squares for gender. Generally speaking, if you don't really care about interactions and you just have main effects, use type 2 sums of squares. From the simulation studies that have been done, it's usually more powerful than using some of the other type of sums of squares. So similarly to type 1 sums of squares, we can visualize this kind of in a model comparison approach. So when we're looking at the main effect of gender, what we're doing is we're comparing two models, right? We're comparing this full model with fluency and gender to it to a model with just fluency in it. And what's ever left over is what we're going to allocate to gender. We do the same thing for fluency. We fit a model with just gender and we compare it to a model with gender and fluency. And what's ever left over is what fluency gets. So we can't use the AOV function. We can't use the regular ANOVA function with lowercase a, but there is a package that we can use that will give us type 2 sums of squares. And that's from the CAR package. And there's a function called ANOVA with a capital A. And this allows you to do type 2 sums of squares, and it also allows you to do type 3 sums of squares. And I also think that supernova from the textbook allows you to do different types of sums of squares. So you could also use that if you'd like. So we can fit our linear model, right, and then feed it into the uppercase ANOVA function. And then we get our ANOVA table. But what I want you to notice here is that the first factor, gender, the sums of squares is different than when we use the type 1 sums of squares. So here it's 2.81. Here it's 3.25. So again, they can give us slightly different answers just because of the models that are being compared to one another to derive these things. The statistics don't really change too much between the two, right? There's still a significant effect of fluency, but there's no significant effects of gender or the interaction between those two. Lastly, and I think probably the most popular types of sum of squares is type 3 sums of squares, or also sometimes called simultaneous sums of squares. This tests main effects and interactions simultaneously. So what I have highlighted here in this Venn diagram is that we have our two main effects and our interaction. They all overlap, right? There's some type of shared variance here. So how do we allocate variance to each of these factors? Well, what we do is we just drop the factor that we're interested in from the equation, right? So we subtract it, and then that's the amount of variance that's explained by that factor. So here we just drop gender from it, and then this is what's left over. And then if we're interested in fluency, we just remove fluency from the equation, and that's how much of the variance is explained. What's important to note here is that it's all explained variance, right? So this is what variance is explained by gender after accounting for the other effects in the model. So this is preferable if you have unequal cell sizes and you care about the interaction. And when we use packages like AFAX, they use type 3 sums of squares under the hood. And I also think if you're using SPSS or SAS or whatever other program you're using, I think it also does type 3 sums of squares. Again, it's important to look into the documentation for these to see what's kind of going on underneath the hood. Similarly to type 1 and type 2 sums of squares, we can look at this in terms of model comparisons. So when we want to know the main effect of gender, essentially what we're doing is we have this full model with all of our terms in it, so the main effects and interaction, and we're comparing it to a model that has gender removed from it. And that's going to be what our sums of squares are for that particular factor. For fluency, we're comparing it to a full model with our main effects and interactions. And we're comparing that to a reduced or null model with fluency removed from that. And then that's going to be what our sum of squares is for fluency. Then we do this for the interaction as well, where we compare a full model to a model that just has the main effects in it. And then that's how we allocate variance to the interaction term. So it gets kind of complicated when we fit these type 3 sums of squares here. So we have to make sure that we deviation code our variable before we run this type 3 sums of squares. It's just sensitive to how things are coded. But we can run the type 3 sums of squares with our ANOVA function, uppercase A. And we can see the ANOVA table here with gender, fluency, and then the gender fluency interaction here with different sums of squares between the type 1 and type 2 sums of squares here. Again, p-values, the inferences that we make are not too different between the two. There's not severe unbalancing here. But just to be aware of the different types of sums of squares and how these things are being partitioned, I think is important. And a lot of time this is kind of glossed over in textbooks, but I think it's still important. And it's highly contentious. People argue about this stuff all the time. My recommendation would be that if you're interested in interactions, you should just use type 3 sums of squares. If you have balanced data, it doesn't matter what's being done. It's going to give you the same results. So. This is kind of an overview or a summary of the different types of sums of squares and what's being done. So type 1 is sequential, right, where we assign maximum variance to A, then to B after accounting for A, and then the rest goes to the interaction. For type 2 sums of squares, the variance for A, or maximum variation for A, only after B is taken into account. For the B factor, the variation allocated to B after A is taken into account. And then the sums of squares for AB after A and B are taken into account. For type 3 sums of squares, the variance allocated to A is allocated to A after B and AB have been taken into account. For the B effect, the variance allocated to B only after A and AB are taken into account. And then for the interaction term, variance is allocated to AB only after A and B have been taken into account. So again, this is kind of the partition of the sums of squares and the different types of sums of squares. It's complicated, it's messy, but again, as I said before, I just want you to be aware that this exists, and to be aware of this when you're fitting your own data. So are there any questions about sums of squares? Type 1, type 2, type 3? Need to mull it over a little bit, think about it a little bit. Yeah. All right, so what I wanted to do is talk about power. So luckily, when we're dealing with categorical by categorical designs, we can use the superpower package, which we've used before in the past. And the superpower package is great, and we can use superpower on our very simple 2x2 design, right? So that's what I am stating here, right? This 2b times 2b is the design that we're using, but it could be extended to more complex designs. So again, as I said, you could do 2x3, 3x5, you could do a 2x2x3, 2x4x5 by 6. You could do all these things with superpower. So it's not limited to these very simple designs. So my recommendation in terms of if you're going to be using an ANOVA type design, to use superpower and perform power simulations to determine the power for your design. And we could do that with the data that we have here. So here we're just going to say that there's 15 participants per group. There's not. I think they're working on creating a function that allows you to have unequal sample sizes and see how that affects power, but I don't know if that is implemented yet. But we're just going to say that there's 15 per condition. We know that there's not. We have to put in our means for each of our groups, which I've done here. And then we have to put in our standard deviations. And then we also have to provide some label names for that. Then we can take all of these objects and we can input them into this ANOVA design. And again, that's going to create an artificial data set for us with our means and our standard deviations for our design. So again, we can see here on the x-axis, gender, and then the y-axis is just going to be quiz performance. And then what we could do is we could take this information and we can perform a power analysis here. So using the ANOVA power function, we just put in our design result object, our alpha level, the number of sims we want. Again, 100 is not enough. We need to run probably 5,000 or 10,000 simulations. Then we can output the results from our power analysis, which we have outputted here, right? So this gives us our power for detecting the gender main effect, the fluency main effect, as well as the interaction between gender and fluency. And this is essentially a post hoc power analysis, right? And we see that there's lots of power to detect the fluency effect, right? That's the only effect that was significant in our analysis, right? And there's low power to detect our effect of gender and also the gender by fluency interaction here. What we can do from this is we can determine the smallest effect size that we can reliably detect at a certain power level. Here, the default is 90%. So by looking at the power here, what's the smallest effect size that we can detect here? And this is just a question open to everyone. So looking at the power and the subsequent effect sizes for those particular effects, what do we notice here? What type of effects can we detect in this data set? So if we look at the first one, power is 94%. If we look at the third row, it's about 79%. But if we look at the first effect size associated with that, what is it? 1.47. So this is Cohen's d. What does a 1.47 Cohen's d represent? Is it small, medium, or large? Anyone remember the heuristics? Yeah, no, Cohen's d of 1.47 is large. And that's kind of the consistent pattern here, right? So there's high power to detect very large effects here. That's what we can find here. And it's my inkling that the effect sizes within this literature, at least, are probably small. So if you wanted to detect an effect or a small to medium effect on quiz performance, you probably wouldn't be able to detect it with this data or with this design. I have some issues with this particular paper. I don't think it should have been published, but that's neither here nor there. I might have to like cut this out of the recording, but yeah, no, so this particular design is severely underpowered, I think, in my opinion. Again, we can only detect large effects, and this literature, there's small to medium effects. So that's what we should have powered this design to detect, which we didn't. But I get it. You're limited in the number of participants that you can run, so I understand. But this is what we can glean from running these type of simulation models, right? We could determine if something is not adequately powered. And I would use this in your advantage, in your favor, when you're reviewing papers. Ask for the data. You can easily run these power analyses, and you can provide some useful information for the authors. So if you don't want to run power simulations, that's fine. So a couple months ago, I ran into this paper that they created a web applet that basically allows you just to draw your interactions, and it tells you how many participants you need, which I think is super cool. So I just wanted to highlight that here. So basically you could go to a website and basically you have, this 2x2 design, and you can just mess around with the bars and it will tell you how many participants you need. So basically you're like, okay, I think I'm going to have like a crossover interaction. How many participants do I need? There's lots of different options here, right? So you can do a between design with two-tailed and then a factorial approach. You could do a mixed design, right? So if you have one within subjects factor and one between subjects factor. What it does is give you the simple effect for A. So these are these blue bars here. So you can state what the actual differences, standardized differences between those two conditions, as well as for the effect, the B effect, which is in red here. So we talked about a knockout interaction last week, right? So this is kind of visualizes the knockout interaction where the effect size is 0 and for A, right, in blue, but there's about a 3.5 mean difference between B here. This is a knockout interaction, and you can see how many participants we need to detect that interaction is 1,025. So it's massive. We talked about crossover interactions. So we could draw our interaction kind of like this, and here we only need 256. So it's important to keep that in mind too, and I'll kind of come back to this at the end. But the type of interaction that you're trying to detect will determine how many participants you need. And always, 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 if you're fitting an interaction model, you're going to need more participants than when you're just trying to fit a main effects model. But I thought that this web applet was pretty cool. So if you want to use this, you can do so. I referenced the paper, and I think there's also an R package for it too, but it's kind of cool. So in terms of reporting results from an ANOVA, make sure you list your main effects and your interactions. So for the main effects, report means and standard deviations, and then also report your significance test, right? So F, degrees of freedom, p-value, and effect size. If your interaction is significant, make sure you follow that up with the simple effects analysis and interpret those simple effects. And then also visualize either the main effect or the interaction. We can use our report function from EasyStats. This can give you some good information that you can then use in your write-up. Again, don't just copy this verbatim. Use this information to guide your write-up for the ANOVA. And this is kind of just a sample write-up of the ANOVA. So there was only a significant effect of fluency. We see here that I state the means and standard deviations for both the fluent and disfluent group. And then I also state that there's no main effects or interactions. So this is just a sample write-up of an ANOVA. And lastly, just some musings on interactions. So number one, avoid them if not theoretically motivated. Just don't throw interactions into your model. Maybe adopt some type of model comparison approach where you compare main effects to interactions, but don't just throw them in there. And the reason why I say that is because they are costly in terms of power and sample size. Depending on the type of interaction that you want to detect, you could need to double or quadruple your sample size. So if we go back to this calculator here, right? So if we wanted a fully attenuated interaction, right, where we're saying that in one effect there's no difference, but then in the other one there is a difference, you need 1,000 participants. That's a lot, right? Again, if you wanted to just find a reverse interaction, 256, that's still a lot, right? I mean, now in the day and age of prolific, I mean, it's not that much, but still, if you're running participants in the lab, that's a lot. And then if we want a partially attenuated interaction, you need 5,582 participants. It's like, holy shit, that's a lot. So these are things that we need to take into consideration when we're trying to look at interaction effects. So if we're going to be looking at a design where we have continuous variables and categorical variables, my suggestion is to center continuous variables so they're more interpretable. Also reduces multicollinearity. And if you're going to use categorical predictors, deviation code. Now, this is really only the case when we're doing like, 2 levels of a factor, right? If we have 3 levels or 4 levels, just use the ANOVA and use m-means, and you do the comparisons that way. Don't try to figure out the coefficients in your linear regression model because it's just going to be a pain. But these are just some suggestions. And then lastly, if we're doing categorical designs and it's greater than 2 by 2, just use an ANOVA and interpret it that way. And my recommendation too is that when you have large models where you have maybe 15 continuous variables and 5 categorical variables, fit the model, the linear regression model, and then just use the ANOVA function to output those results, because that will give you the main effects for those categorical predictors, which you can then follow up with m-means and get the pairwise comparisons for those conditions. That would be my suggestion, at least, when we're dealing with very complicated designs. So it's funny, I started out at the beginning of the semester saying no ANOVA, just everything regression, and I end with you should use ANOVA for interpretability, to make your life easier sometimes, but that's how it goes sometimes. Nothing is ever simple. So that's all that I have. Are there any questions about ANOVA, about power? Sums of squares? So I know it's a lot to take in. On Wednesday, we have a lab that will hopefully kind of solidify some of these things, and make things a little clearer. So that is all that I have. If you don't have any questions, you guys are free to go. For those of you that came in late, here, final paper, due final exam week. I'm going to create a GitHub repository for you to use. So that's going to be similar to our labs, where there's going to be a link, you click on it, and that's where I want all of your materials to reside for the final project. And again, it should be reproducible, so I should be able to reproduce every single thing in your paper. So tables, figures, references, everything. And then if you have any questions about it, just post via the issues button in the repository.